All right, let's do some problems related to derivatives in graphing, using derivatives to analyze the graphs of functions. Looks fun. Alrighty. Find the global extrema of h of x equals 2x minus 3 over x squared on this interval. All right, we've got a closed interval, which is telling me that I probably want to use the closed interval test, also known as the candidate's test. Global extrema. Also, I'm just going to think about my function for a second here. H of x is not defined at x equals 0, right? Because you would have a vertical asymptote there. But that's not in my interval, so I'm not too concerned about that. So this function, h of x, is going to be continuous on this closed interval, which means the extreme value theorem applies. And that means that it has to have a max and a min. So what I need to do is I need to compare h of 1, h of 6, and h of any critical points. So let's find the critical points of h. So h prime of x, you know what, I think I'm going to simplify h first and say that h is just 2 over x minus 3 over x squared, which is 2x to the negative 1 minus 3x to the negative 2. So h prime of x would then be negative 2x to the negative 2 plus 6x to the negative 3. I'm not sure if this is the faster way to do it, but that's fine. So that is going to be negative 2 over x squared plus 6 over x cubed. Common denominator is x cubed, so I should get negative 2x plus 6 over x cubed, because I multiplied this by x over x so that I can get a common denominator. Okay, so that should be my h prime. So critical points are where the derivative is 0 or undefined. So undefined, or 0 rather, would be where negative 2x plus 6 equals 0, and that's going to give me the solution of x equals 3. Undefined would be where x cubed equals 0, and that would give me the solution x equals 0. But remember, x equals 0 is not in the domain of my original function because it's a vertical asymptote, so I do not need to consider this point as a critical point. Besides, it's not on my interval, so who cares? Now I need to compare h of 1, h of the critical point or points on my interval, and h of 6, and just see which one is the largest and smallest. Well, h of 1 is negative 1, h of 3 is 1/3, and h of 6 is 9 over 36, which is 1/4, I think. Hopefully my mental math is correct there. And so I would say h has a global or absolute max of 1/3 at x equals 3, and a global min of negative 1 at x equals 1 on the interval 1, 6. Right, it's on the closed interval. So I think that would be my conclusion there. Notice that it says find the global extrema, so I do need to actually find the y values, which were 1/3 and negative 1. All right, number 2. Looks like I had a little bit of some error when I converted this thing. That shouldn't say cosine twice. That's just an error there. Look at the absolute extrema of the function f of x equals 3 cosine x over this interval. Again, candidate's test / closed interval test. So let's find f prime so I can find any critical points on the interval. That would be negative 3 sine x. Negative 3 sine x is equal to 0, where sine x is equal to 0. And of course, sine x equals 0, where x equals, well, 0, pi, 2 pi. But on this interval, we would have x equals pi. Okay, I'm not going to make a sign chart or anything because, again, this is the candidates test, the closed interval test. So now I'm just going to find f of pi halves, f of pi, and f of 3 pi halves, and see which one is the largest and the smallest. Plugging in pi halves, cosine of pi halves is 1, so that's going to be 3. Cosine of, wait, that's not right. Cosine of pi halves is 0, so that's going to be 0. Cosine of pi is negative 1, so that is going to be negative 3. And cosine of 3 pi halves is again 0. So we have an absolute max of 0 at x equals pi halves and 3 pi halves, and an absolute min of negative 3 at x equals pi on the interval pi halves to 3 pi halves. Find the difference between the absolute max and absolute min values of this function on this interval. Again, candidates test. All right, well, let's see. F prime of x would be, well, let's see. This is 3x to the 1/3 minus 4x. So that would be 3 times 1/3 x to the negative 2/3 minus 4. So that is x to the negative 2/3 minus 4. Okay, I'm going to combine that into one fraction because that's what I like to do. 1 over x to the 2/3 minus 4 over 1. So that's going to be 1 minus 4x to the 2/3 divided by x to the 2/3. So that's my derivative. Now, this derivative is 0, where 1 minus 4x to the 2/3 equals 0, which means that x to the 2/3 would equal 1/4. Now, x to the 2/3 is the cubed root of x squared. So if I cube both sides, I get x squared equals 1/64. Pretty sure I've done this problem before, but that's fine. Take a square root, I get x equals plus or minus 1/8. And where is f prime undefined? F prime is undefined where x to the 2/3 equals 0, which is that x equals 0. So those are my critical points, 0 plus or minus 1/8, but I'm just going to use the ones that are on the interval. So I need to compare f of 0, f of 1/8, and f of 1 and see what I get. F of 0 is pretty clearly 0. The cube root of 1/8 is 1/2, so that's going to be 3/2 minus 1/2, which is 1. And f of 1 is 3 minus 4, which is negative 1. So the difference between these two, the max and the min, is 2. 1 minus negative 1 is 2. Given this function, find all c in the interval 2, 7 that satisfy the mean value theorem. The mean value theorem says that f prime of c has to be equal to f of b minus f of a over b minus a. So that's the equation I need to be thinking of with the mean value theorem. So they want us to find c. So I need to find f of b minus f of a over b minus a and set it equal to f prime of x to find my c values. So let's see here, 2, 7. Well, f of 7 is equal to 9 minus 2, which is 7. F of 2 is equal to 9 minus 7, which is 2. That means that f of 7 minus f of 2 divided by 7 minus 2 is just equal to 7 minus 2 over 7 minus 2, which is equal to 1. So the average rate of change on this interval, or the slope of the secant, is 1. Now I need to find f prime of x. F prime of x is equal to 0. Remember that this is 9 minus 14x to the negative 1. So if I find the derivative of that, I should get 0 plus 14x to the negative 2, which is 14 over x squared. Okay, so I know that f prime of c, which would be 14 over c squared, has to equal 1, right? I found f prime of c, I found f of b minus f of a over b minus a, and I'm setting them equal. That should give me 14 equals c squared, so c equals plus or minus root 14. Now, this has to be on the interval 2, 7, so I'm going to choose just the positive root 14 and not the negative root 14 because it's not on that interval. So essentially, I've got some function, right, from 2 to 7, the slope is 1, and I found the point where, right, an x value of root 14 where the tangent was parallel to the secant. Consider this function. Okay. Determine whether the mean value theorem applies to this function on this interval. Be sure to state each condition precisely. If the mean value theorem applies, find the value of c which satisfies the mean value theorem. This looks like a piecewise function. I'm wondering if it was on 2 lines and the formatting got messed up when I changed it. But in any case, we've got one piece, 6x plus 1 for x is less than 1, and then x squared plus 4x plus 2 for x is greater than or equal to 1. So the mean value theorem applies. I need f to be continuous on the interval 1, 5, closed, and I need it to be differentiable on the open interval 1, 5. It doesn't have to be differentiable at the endpoints. So we got to check that. So first of all, if I plug 1 into both pieces, I get 7, right, if I plug it in here. Does it equal, plug 1 to the other side, I get 1 plus 4, 5, 6, 7. Yes, it's continuous. In other words, the limit from the left and the limit from the right are equal. So I could say the limit as x approaches 1 from the left of f of x is equal to f of 1, which is equal to the limit as x approaches 1 from the right of f of x, and all these things are equal 7. So that means the function is continuous at 1, and therefore continuous everywhere, because I know that the linear function is continuous and also the quadratic. Now I need to find f prime of x and see if the function is differentiable at 1. Wait, do I need to see if the function is differentiable at 1? No, I actually don't. Reason being is my interval is 1 to 5. So if my interval is 1 to 5, I actually don't need it to be differentiable at the endpoint. So I can just focus on this function because this is the function for x is greater than or equal to 1, and I know that function is differentiable. So this is differentiable on the open interval 1, 5. So I don't even really care whether this is differentiable at 1. Just out of curiosity, is it? Well, f prime would be equal to 6 for x is less than 1, and 2x plus 4 for x is greater than or equal to 1. So it's even also differentiable at 1, but again, I don't really care. So now I need to find c such that f prime of c is equal to f of b minus f of a all over b minus a. Again, where a is 1, b is 5, and c is what I'm going to find. So f prime of c is going to be 2c plus 4, and I want that to be equal to f of 5, which is 25 plus 20 plus 2, minus f of 1, which is 1 plus 4 plus 2. That's all divided by 5 minus 1, which is 4. So that gives me 2c plus 4 is equal to 47 minus 7 over 4. So 2c plus 4 is equal to 10. 2c equals 6, c equals 3. So that is the place where the slope of the tangent is equal to the slope of the secant. Let g be a function that is differentiable for all real numbers. The table below gives the values of g and its derivative g prime for selected points x in this closed interval. Find a positive real number r having the property that there must exist a value c with 0 less than x less than 0.5 and g double prime of c equals r. I have to think about this for a second. Okay, I see. So this is sort of like the mean value theorem, but applied one layer down. So really what we're looking for is we are looking for we are looking, I see, we're looking for essentially what g prime of 0.5 minus g prime of 0 divided by 0.5 minus 0, what is this equal to? This is the average rate of change for g prime on the interval 0 is less than or equal to x is less than or equal to 0.5. And we know g double prime has to equal that value by the mean value theorem, right? And that's because this function is differentiable. The only thing that's a little tricky here is I think it would really need to say that g prime is differentiable as well. I guess I'm questioning if g is differentiable, will g prime be differentiable? Maybe. I'd have to think about that. But in any case, let's assume for now that g prime is differentiable. And so if g prime is differentiable, if we find the average rate of change, we know that g double prime has to equal that at some place. And so that's going to solve this equation because we're finding the average rate of change of g prime, and g double prime is going to have to equal that. So this value is equal to, let's see, g prime of 0.5 is 3, and g prime of 0 is 0. And that would be over 0.5. So 3 divided by 0.5 is 6. So that means g double prime of c has to equal 6 at some point, and r then would equal 6. Okay? For what value of x does this function have a relative maximum? Well, to find a relative maximum, we would need to find the critical points. To find the critical points, we would need to find the derivative. I'm not sure whether it's easier to use the product rule or multiply out. I think I'm going to choose to multiply out. So f of x would be x minus 2 times x squared minus 6x plus 9. So that is x cubed minus 6x squared plus 9x minus 2x squared plus 12x minus 18, which is x cubed minus 8x squared plus 21x minus 18. Therefore, f prime of x should be equal to 3x squared minus 16x plus 21. Okay, setting that equal to 0. Let's see if we can factor it. 3x times something and x, or 3x plus something and x plus something. And these second two numbers need to multiply to 21. So probably 7 and 3. Let's see. Is this going to work? 3x and x. 9 and 7. Okay, I can do maybe minus 3 and minus 7. Negative 9 minus 17. Yeah, that's the correct factorization. So my critical points are x equals 7/3 and x equals 3. So now I need to see whether the function f prime changes from positive to negative or negative to positive. Since I want a relative maximum, which on f looks like this, I want the derivative to change from positive to negative because that tells me the original function is changing from increasing to decreasing. So here's 7/3, here's 3, so I could test maybe 2. Wait, no, 2 is not more than 7/3. So let's test 2.5. Over here I can test 0, and here I can test 4. So let's see what the signs of f prime are. If I plug in 0, I'm going to get a positive value. If I plug in 2.5, I'm going to get a positive times a negative, which is negative. Plug in 4, I'm going to get a positive. So f is increasing, then decreasing, then increasing, and therefore I should have a max at 7/3 since f prime changes from positive to negative. And you can see the graph is going to look like this. All right. Whoopsies, this got pushed to the next page. The graph of y equals f prime is shown on the right. For what values of x does f have a local maximum? Justify your answer in a sentence. A local max is where the derivative changes from positive to negative. Since this is f prime, there are two places where the derivative changes from positive to negative. F has relative maxima at x equals 2 and, negative 2 and x equals 3, since f prime changes sign from positive to negative at those points. First derivative tests. All right, for what values of a and b does this function have a local maximum when x equals negative 3 and a local minimum when x equals negative 1? All right, well, let's find f prime and set it equal to 0 and see what we can figure out. Finding f prime gives us 3x squared plus 2ax plus b. Okay. When we plug in negative 3 and negative 1, we want this to be 0 because, why? Because they're critical points, and this derivative is never undefined because it's just a quadratic. So the derivative would have to be 0 at these points. So if we plug that in, we'd get 27 minus 6a plus b, and that needs to equal 0. And if we plug negative 1 into f prime, we get 3 minus 2a plus b, which also has to equal 0. So now we have negative 6a plus b is equal to negative 27, and negative 2a plus b is equal to negative 3. So let's subtract this from the top, and we should get negative 4a equals negative 24. And so a is going to equal 6. If a is 6, then negative 36 plus b equals negative 27. So b is equal to 9. So those should be the values that will give this a local maximum and minimum of these points. And of course, f of x is a cubic that looks like this. So for sure the maximum is going to happen at negative 3 and the minimum at negative 1. We could show that, but I'm just going to stop at that point. 10. A function f is continuous on the closed interval negative 3, 3, such that f of negative 3 is 4 and f of 3 is 1. Okay. The functions f prime and f double prime have the properties given in the table below. Okay, so they're telling us where the derivative is positive, negative, undefined, 0, etc. What are the x-coordinates of all absolute maximum and absolute minimum points of f on the interval negative 3, 3? Justify your answer. Interesting. All right, well, closed interval, candidates test. So first of all, we need to compare f of negative 3, which is 4, and f of 3, which is 1, with any critical points. Now, critical points are where the derivative fails to exist or is 0. By the way, this function is continuous, so we know the EVT applies, right? It has to have a max and a min. And that tells us that this is not like an asymptote or something, because the function is continuous. So it's got to be a corner or a cusp. So, okay, so we know that's a critical point, f of negative 1. And we also know that there's a critical point at 1. But we don't know their exact values. What we do know is that from negative 3 to negative 1, the derivative is positive. So that means this value has to be 4 plus, right? It's got to be bigger than 4 because the function must have been increasing since the derivative is positive. Okay. Then between negative 1 and 1, we've got a negative derivative. So that means that the function is decreasing. And it turns out it continues to decrease from 1 to 3. So we know this is less than 4, but it has to be greater than 1 because it decreases from there to the next point. So let's say, I don't know what these are, but this could be like 5, and this could be like 3. So what we know for sure is that the absolute max occurs, I don't know what it is, but it occurs at x equals negative 1, and the absolute min occurs at x equals 3. And sort of for the reasoning that I put in here, right? I'd probably want to write a sentence about increasing and decreasing, but in the interest of time, I'm going to keep moving. What are the x-coordinates of all points of inflection? Okay, points of inflection are where the second derivative changes sign. I need f prime to change sign, because if f double prime changes sign, then I have a point of inflection because f is changing concavity. So it looks like the point where that occurs is at x equals 1, since f double prime changes sign at that point. Okay, so the original function is going to go concave up to concave down. Alrighty, if f double prime of x equals x times x plus 1 times x minus 2 squared, then the graph of f has inflection points where x equals, well, inflection points are where this changes sign. This is f double prime, so it has to change sign. Now, I don't know what you know about multiplicity of roots, but what I know is if the multiplicity of the root, if it occurs once or 3 times, then you're going to cross the x-axis. But if the multiplicity of that root is 2, if it happens twice, then you're not going to cross the axis. So that means, whoopsies, this function right here changes sign at x equals 0 and x equals negative 1. But not at x equals 2. Okay, if I were to draw f double prime of x, it has zeros at 0, negative 1, and 2. Okay, it's a 4th degree polynomial, and it opens up. So it's going to come down like this, go straight through, then it's going to bounce off the axis because of the multiplicity 2. So this is f double prime. So you can see that f double prime is positive, then negative, then positive, and then positive again. So that's a point of inflection right there, and so is this, but not this, right? Because the f double prime does not change sign. So that is going to give us the solution of negative 1 and 0 only. Okay, f of 3 equals 4. F prime of 3 equals negative 5. Okay. F double prime of 3 equals 2. G prime of x is equal to, my goodness, this is complicated, x squared minus 7 times 5f of x plus 4f prime. My goodness. Does G have a local max, min, or neither at x equals 3? Oh my goodness. Well, we better find what G prime of 3 is. Well, G prime of 3 would be 9 minus 7 times 5 times f of 3, which is 4, plus 4 times f prime of 3, which is negative 5. So I'm checking to see if this is 0, because if it's not 0, then it's not going to be a local max or min. That's 2 times 20 minus 20, which is 0. Okay, so this is a critical point for G, because G prime of 3 is 0. So that's our first check. Now, we need to figure out whether this is a max or a min. Because we don't have any values like, we don't know f of 2, we don't know f prime of 2, or maybe f of 4 or f prime of 4, the first derivative test is probably not going to work, because we're not going to be able to tell whether G prime changes from positive to negative. So that's telling me I better try the second derivative test, okay? Because there's no way to see whether G prime is changing sign, because I just don't have that information. But maybe I can find G double prime and see whether G double prime is positive or negative. Now I'm really hoping it's positive or negative and not 0, because if it's 0, I'm going to be stuck again, because then the test is inconclusive. But I'm guessing it's going to give us a positive or negative value. So let's find G double prime of x. Now G double prime of x, I'm going to have to use the product rule, because I have one function here times another function here. Okay, so let's find the derivative using the product rule. It would be first times the derivative of the second. Now the derivative of the second is just going to be 5f prime plus 4f double prime. Another hint that I'm going to use the second derivative is because they gave me f double prime, so I'm assuming I'm going to use that. I got to finish my product rule here. Of course, I did first, derivative second. Now I need to do plus the second, which is 5f plus 4f prime times the derivative of the second, which is 2x. Nice. Okay, good. So now I got to find G double prime of 3 and see what it equals. Well, it equals 2 times, 5 times f prime is negative 25, plus 4 times f double prime, which is 8, plus, 5 times f is 20, plus 4 times f prime is negative 20. Hooray, that's 0. And then I get 2 times 3, which is 6. So I'm going to get 2 times negative 17 plus 0, which is negative 34. Yay, that's good. So what I know is, since G prime of 3 equals 0, and G double prime of 3, which equals negative 34, is less than 0. Okay, so I have a horizontal tangent, and my second derivative is negative, which means the function is concave down. So at x equals 3, it looks like this, the original function g, right? I have a horizontal tangent, nice, and the function's concave down. So that means that g of 3 is a local max. Nice. By the second derivative test. Lovely. Yes. Okay. 4 of 7. Okay, we're cooking along here. The graph of f prime is given. Use the graph to identify the critical numbers of f. Okay, this is f prime. So I got to make sure I know what I'm looking at. So critical numbers of f, or f prime is 0. X equals -3, x equals 1, x equals 5. Since f prime of -3 equals f prime of 1 equals f prime of 5 equals 0. I don't care that they're equal, but I do care that they're all equal to 0, so that's just an efficient way to write it. Determine whether f is a relative max or relative min at each critical number. Okay. F has a relative minimum at x equals -3 since f prime changes from negative to positive. So therefore, f is going from decreasing to increasing. Great. F has neither a relative max or relative min at x equals 1 since f prime does not change sign. Okay, so that's going to be positive to positive, increasing, horizontal, increasing. So increasing that whole time, of course, because it just has that one spot where it flattens out for a tiny second. Oopsie daisy. Okay, and f has a relative max at x equals 5 since f prime changes from positive to negative. So the original function goes from increasing to decreasing, and I would have a relative max. Great. Alrighty. Determine the intervals where the graph of f is concave up and concave down. Okay, f is concave up where f double prime is positive, which means that f prime is increasing. Concave down where f double prime is negative, and therefore f prime is decreasing. So f is concave up where f prime is decreasing, and that's decreasing from, it looks like, -2 to 1, and from 4 to positive infinity. F is, however, concave down where f prime is increasing, and that would be from negative infinity to -2 and from 1 to 4. Great. The graph of f prime is given. Use the graph to determine the x-coordinate of the inflection points. Justify your answers in a sentence. Okay? This is f double prime. F double prime. So where f double prime changes sign is where f has points of inflection. So f has points of inflection at x equals -4, x equals -1, since f double prime changes sign at those points. Notice that it does not have one at x equals 3 because the second derivative does not change sign. By it, I mean the original function. The original function does not have a point of inflection at x equals 3. Okay, fill in the chart with positive, negative, or 0 for each of these points for f, f prime, and f double prime. I am looking at f, so make sure you know what you're looking at. F at point A is negative because it's below the x-axis. At point B and C and D, it is positive because the function is above the x-axis. Now f prime. Now we are looking for whether the function we're looking at has positive slopes, zero slopes, or negative slopes. At A, the function is increasing, therefore f prime must be positive. At B, it has a horizontal tangent. By it, I mean the original function, and therefore f prime should be 0. At C, the function is decreasing, therefore f prime is negative. At D, the function is increasing, therefore f prime is positive. Now, f double prime is concavity. So is it concave up like a cup, or concave down like a frown, or is it a point of inflection? This whole section right here looks like it is concave down, right? Any tangent line that I draw is going to be on top of the curve, right? Above the curve of sorts. It's concave up, down like a frown. I don't know if I said up, but I meant down. And then we can see from here, the function is concave up like a cup. And the tangent lines are now below the curve, right? So we can see that it is concave up there, the original function. Alrighty, that's good. So that tells us that at point A, the second derivative must be negative because the original function is concave down. The slopes here are positive, but getting less so. Here, the slopes are negative and getting more so. So at B, the second derivative is still negative. Remember that you can definitely have a second derivative that's negative where f prime is 0, right? Think about the graph of f prime. It could pass through the x-axis but have a slope that's negative. So therefore f prime can be 0 while f double prime is negative. It's kind of uncommon for them both to be 0. I mean, that's also possible. Okay, at C, that looks like a point of inflection, so I'm going to say that the second derivative is 0 there, changing from concave. F is changing from concave down to concave up. And D, that point, the original function is concave up, so therefore the second derivative must be positive. Okay. Six of 7. The graph of the derivative of f is shown in the figure below. On the same set of axes, sketch the graph of f. Okay, so I'm looking at f prime. I want to graph f. Alrighty. F prime looks like it is at 2 for a while. So therefore, f needs to have a slope of 2. So I don't know exactly where it starts. Let's just say it starts here. And it needs to have a slope of 2. So I need to go down 3 over 1.5. So it would look like this. Now it could be anywhere, but it needs to have a slope of 2. Now here, it looks like we have a bit of a quadratic situation because this line looks like, well, it is the equation of 2x. So therefore, the antiderivative, we would call it, or the original function, should be x squared. Now, it could be x squared plus something, or it could just be x squared. Let's say it's x squared plus 2, because then I can match it up here. Okay, and it's going to look like that, basically. It's quadratic there. Also, you can see that where the derivative is negative, right here, the original function should be decreasing, which it is. This is kind of a challenging problem. And then where the derivative is positive again, it should increase. Okay, so from that point right there, we're back to a slope of 2, right? F prime of x equals 2. So therefore, we must have a function that is 2x plus something. Just because I feel like making this continuous, I am going to just draw it right there. So it doesn't have to be continuous because it doesn't tell us that, but it would look like that. If I was writing the equation for f prime, I would see that it is 2 for basically x is less than -1. Then it is 2x for -1 is less than x, which is less than 1. And then it is 2 again for x is greater than or equal to 1. So that means my original function should be something like 2x plus b. I don't know what the b value is for x is less than or equal to -1. X squared plus, I don't know, c for x. Sorry, -1 is less than x is less than 1. And then 2x plus d for x is greater than or equal to 1, right? I don't know what those constants are. I just kind of made it so that they meet. But that is a challenging problem. Yeah, I like that one. Given the graph of the derivative of f prime, which of the following would correctly depict a possible graph of f? Okay, f prime. F prime is negative and getting way more negative. And then it becomes very positive and getting less positive, okay? So those are the y values of this function, right? They're just a little bit negative, but getting way more negative, and then they're super positive and getting less positive. So a little bit, why is my pen not working? A little negative, and then way more negative. Okay, and then we are v positive, and then a little bit positive. Okay, so on this thing, the function should be increasing because the derivative is positive, and over here, f should be decreasing. So I'm not even going to look at the graphs until I do that. So it decreases not very much and then a ton. So, and then it increases a ton and then not very much. So that looks like this, okay? Decreases a little bit here, decreases a ton here, increases a ton here, increases a little bit here. So that looks like it would be B. Okay, this doesn't work because here the function is increasing when it should be decreasing. Here, again, the function increases when it should be decreasing. Same thing here. So really the only function that decreases where it should decrease is B. Following graph of G and G prime. For which of the following graphs is G prime, that's a little prime there, is G prime greater than 0 and G double prime greater than 0? Okay. Choose all that apply. Consider the following graphs of G and G prime. Okay, G prime. Is it greater than 0? Yes, G prime of x is greater than 0 because the y values here are positive. It's above the x-axis. G double prime would be less than 0 because G prime is decreasing. So yes. Here, G of x. Okay, G prime of x would be greater than 0 because G is increasing. G double prime of x would be less than 0 because G is concave down, aka G is decreasing, right? So G is decreasing there. The slopes are positive, but getting less so as we move from left to right. And here, G prime, is it positive? Yes, G prime is positive because it's above the x-axis. However, G double prime is also positive because G prime is increasing. So those two have this characteristic where G prime is positive and G double prime is negative, but this one does not. What that tells us about G is that G is increasing and concave down. So that's this graph right here. And what it tells us about G prime is that it's positive and decreasing, which gives us this graph right over here. So yes, those two things, for those two functions, this would be true. What a great problem. All right, it looks like that's it. Hope you enjoyed.